second session of day 3 for this 5 days STTP. And as we have witnessed with the progress of sessions, the depth of concept has been proliferating. So to continue with that, we will be having another wonderful session by our prominent speaker, Dr. Svetlana Brizev, who will be presiding over the topics of macro modeling approaches, including wide column model and equivalent truss models. So over to you, ma'am.
Yes, thank you very much, Aditya. I think I'm not able to share. Can you see my screen, my slide?
Yes, ma'am.
Yes, ma'am.
I cannot get into presentation mode. Okay, so just let me presenting, give control. No, I don't need to give control. So it's not in a presentation mode, unfortunately. I'm not sure why, but I will continue with how it is. So it is not somehow I don't have a control over the. Stop sharing. I'll try again. Let me see. There seems to be some problem with the presentation mode. So I'm sharing. Not sure. Can you see my presentation or not?
Yes, ma'am.
Okay. Okay. Now I'm okay. I was looking at a different screen. I apologize. So good afternoon, everyone. I think I will switch off my camera. It seems my internet is a little bit unstable, so it's better to keep camera off during the presentation. After during the lectures, I can switch it on if you don't mind. Can you hear me? Am I audible properly?
Yeah, absolutely fine.
Okay, perfect. So the topic of today's lecture is finally, I know many of you are interested in modeling of confined masonry buildings. So finally, we are coming to that topic, and I tried to, in this lecture, to give an overview of different modeling approaches. Plus, I shared 4 relevant papers, which I hope you received, which are explaining in more details the modeling, and they were published in the leading journals, and they were developed mostly in India or with Indian students at IIT Gandhinagar. So over the last few years. So the macro modeling approach, the first question is we will try to answer about general modeling. It's nothing to do with confined masonry, but it's a topic of modeling of actual buildings for structural analysis. And these are my thoughts, opinion. It is a challenge. It may be a challenge. It is combination of science and art because it is not always straightforward to do modeling. In some cases, it is more logical or straightforward than in the others. For example, for frame structures, it is simpler than for wall structures. Masonry buildings are more challenging to model than reinforced concrete and steel frame buildings, and various approximate methods are needed for modeling. They may not be always approximate, but we use approximate methods as well as more accurate methods. It all depends on the application. So what we are, the focus will be first of all on 2D modeling. If you have a plan of the building like shown on the top diagram, this is actually from reinforced concrete building, but it does not matter. And we are trying to isolate one of the frames and which is shaded, which is shown hatched A, B, C, D. So if we cut it out of the structure and we apply, let's say, seismic forces, we can then model this, even though this frame contains also a part of the slab. Let's say we have a reinforced concrete columns and slab system. So if the slab is there, that slab is also modeled as a beam. Or maybe there is a beam at the location of the columns, but there is also a slab. So we need to model not only a beam, but also a slab portion, and that is the so-called beam slab element. So these are evolution of this. This is evolution of this model. So diagram C shows how we model based on the center line of the columns and the slab. And then D is a linear line model, which ultimately we use to enter into our software, such as SAP 2000 or any other software that we use for analysis. Okay. So this same concept, I'm showing it, in fact, it is from a reinforced concrete design textbook, which I co-authored. That is one of the diagrams from that book. But anyways, I want to show that as a concept, it does not matter whether we are talking about reinforced concrete or masonry structures. And I would like to say that I believe that 2D models are very useful. I like and I do 3D models, of course, of structures, but 2D models are much more to start with. They're easier to comprehend and to understand the behavior than and to find the errors in modeling than 3D models. So it's always good, even if we are doing 3D model and we are starting with something new, it's always good to start with a 2D model of a structure. I think it's maybe this recommendation is not maybe popular, but it is, I believe, very important. So if we do 2D model, now going back to the previous one, but we know, okay, we isolated one frame. What about other frames in the building? Like, this is just a partial floor plan, but maybe there could be 10 grid lines in this building. It could be a large building. So what do? We practically build a model by putting the adjacent parallel frames together in 2D plane. So that is shown on the next diagram. So we have here models for different frames 1, 2, and 3, which are all in the same plane, and there are rigid links. Unfortunately, yeah, on this diagram, links are not shown as they should be. It looks like they're pin connections, but they are pin connections, but they're pinned at the end of each link. So you have two pin ends, and the connections at the ends of the frames are rigid because frames have rigid connections between beams and columns. So that is a small effect. Maybe on my I may correct that slide. That is slide number 4 in my handout. I will correct it so that it is that you get. I will update this for your evidence for after the lecture. Okay. So, anyways, but the concept is the same. So the point here I'm trying to make is that if you have 10 frames, you could always put them in 2D plane, and you can apply a story shear force, lateral force loading at each floor, and it will be distributed to these frames correctly in the same way as it would be in 3D model. Now, how is that possible? Well, it is possible because each of these frames has its own stiffness, and the forces will be distributed according to the stiffness, assuming that we have rigid floors, obviously, and whether they're in 2D or 3D model. The only thing that it will not be considered is that if we have a torsion in the model, that cannot be taken into account directly with this 2D model, except if we have some way of calculate increase in the loading due to torsional forces and then apply that in a model. So, but if we don't do that, then this model will be good for symmetrical, the structures that are symmetrical in plan and they don't have torsional effect. So even if the building is non-symmetrical, which is commonly the case, it will give us a good sense of the distribution of forces in this building. And that is, I think, very important. So what I would like to say, I believe that both 2D and 3D models are necessary for a complete understanding of complex structures. So in any case, this is the starting point, and I purposely wanted to do, because with a 3D model, I have nothing much to say. You have a slab, you model it as a slab, you have a wall. We will see now how you model the walls in this, according to this macro modeling methodology, and so on. So that is it. But for 2D model, there is additional explanation. And as I said, I'll just update this slide 4 to clearly show these rigid links that I'm talking about. And this purpose of these rigid links between this frame 1 and frame 2 and frame 3 is just to share horizontal forces. So they're like truss elements with pin ends, and they can only transfer horizontal forces. They cannot transfer bending moments or shear. So that is the whole idea of these rigid links. So that's why you're just taking a share of horizontal loading on each frame, transferring it or sharing this horizontal loading, which we apply just one force at the left side of this to the system, and then it will be shared among all these frames. So this is a very efficient and effective way of modeling. It, of course, may be more time consuming than just 3D model, but it is possible once you have the properties of the elements. Now, the main topic is macro modeling approaches for confined masonry buildings. The topic was confined masonry. So we will talk about wide column model, which is also known as equivalent frame model, particularly in reinforced concrete structures. So the model is coming from reinforced concrete structures. It's called equivalent frame model. The second is strut and tie model, which is for limit analysis, ultimate limit analysis only. And then the third is equivalent truss model for both linear and nonlinear analysis. So the second model, strut and tie, is just not simply a modeling approach, it is modeling and design approach. And that's how it is recognized by the new Indian confined masonry code. So let us start with the wide column model. What is it? We have here a wall. This could be a reinforced concrete wall. I know you are designing or will be designing many concrete walls with openings. Let's say it has some door openings. So this is so-called coupled wall system, and you have two walls and an opening, maybe an elevator course. And what we do is, instead of one way would be, of course, to model this as a as a plane structure with plate elements, and you could directly model it as we can see it on the left-hand side. But an alternative way of modeling, which has been popular for the last 40 to 50 years, I mean, at least it's been published at that time and used since that time, 1970s, so to speak, is the model. You can see Stafford Smith paper from 1970, so it's 52 years ago. So anyways, this model is so-called equivalent frame model in the literature related to reinforced concrete frames. And it consists of these two walls are modeled as two vertical elements, like two columns. And here is the title, the name wide column, because these columns are very oblique. They have a large length. Length of the column is equal to the length of the wall in cross-sectional dimension, and then thickness, the other dimension, is equal to the thickness of the wall. So these are two vertical columns. And then the horizontal element, which is basically a slab, there would be some slab going on top of the walls at each floor level. So we model a part of the wall of this horizontal element as a rigid element. This is not rigid link, it's just rigid element. It's rigid portion of this horizontal element. And that is equal to the width W of this column from the center line to the opening. And then the part that is within the opening, we model, this is with L, labeled with L, we model it as a slab element, because there would be a slab, or maybe it's a slab and beam element if there is a beam as well. So anyways, there are two different stiffnesses associated with the part of the wall that is within within the length of the wall. And then another property, so we have two properties, one is rigid and one is beam, as you can see, rigid arm, or you can call it a rigid element. And then beam element has the exact properties. So later on I will talk maybe how to simulate this high rigidity, what are the ways that at least I do in modeling, or I recommend to the students. But right now let's leave it at that one is infinitely rigid. So you can see I, moment of inertia, times area is infinite, whereas for the beam element, we call this rigid element and beam element, it is EI, it is the exact properties of this element, and it's entered with those properties in the model. So, the idea is, so that is what it looks like. White column model is equivalent frame model. So what it shows is that basically we have, if we forget about these rigid elements and non-rigid elements, we have basically we have a frame model. So out of the wall, we created a frame. So that's why it's called equivalent frame model. Now, the idea is that connections between beam columns, wide columns, and these horizontal elements, beam elements, are rigid. Therefore, we would have a bending at the interface. You can see the left-hand side deformed shape of this horizontal element with these two center lines. Because the rigidity of this portion over the length W is very high, so rotations will be very small in that portion, and much larger rotations will be over the portion L, which is the normal, so to call normal element with the actual. So this is simulated rigid element is exaggerated rigidity, and this L element has the actual rigidity of that slab. Let's imagine that we have just a slab there, but as I said, it does not matter. It could be also a beam and slab. So this is now from again this use of a wide column model, of extensive column model, to my knowledge, for as far as confined masonry is concerned, as most papers are coming from Mexico, but I believe it's been used for any in all the other countries that use confined masonry and engineered confined masonry buildings, such as the ones that Professor Juan Jose Perez Gavilan talked about. So this is from another paper by another professor from Mexico, Amador Terran Gilmore, and who published very interesting papers also about modeling. He's more into modeling of confined masonry, not experiments. And this is a nice diagram from one of his presentations, where he shows on the left-hand side an actual confined masonry wall, or one line of walls. We have more than one wall here, but let's say one grid line, along one grid line. This is solid wall, then there is a door opening, then there is another pier, a small wall, then there is a window opening and another wall. So how do we model it? This solid wall on the left is modeled as a wide column, which is shown as black here. And then these other two walls are also modeled as wide columns, which are shown as black. Now, these horizontal elements are the blue colored ones are these rigid wing elements. And this is nice drawing on the right-hand side, nice diagram, because you clearly see what is the actual wall and what is the length of these rigid elements. And then the red colored elements are showing the actual, these slabs, let's put it, if it is a slab at that location. If you don't have beams, then it is just a slab element, or it could be slab beam element. Okay, so so that is what it is, and this and I will talk separately or in more detail about modeling of these parapet portions of the wall. You can see here, for example, that there is another black element in the middle of this, below the opening here, below the window opening, which models the parapet. and then another rigid element which models this parapet portion. So because parapet portion of the wall below the opening is also rigid, so if you want to get a more precise design or simulation of the behavior, then it is needed to simulate the behavior of this parapet as well. But it is not necessary. So we have different levels of complexity of the models. I would say that this is not the basic level of complexity, it is more advanced model. A less advanced would be to ignore or somehow in a more simplistic way model these parapets below the windows. For the doors, that is not an issue. It is more for windows. I think next slide is extra. It is the same as, I think I should remove it. So I'll definitely update the presentation. Sorry about that. Slide 10 I will remove because I already explained that. It was I would say pioneering work by Stafford Smith. And this is now what we want to talk about. So how do we simulate, let's say on a simple case of a simple solid wall without openings? Solid wall means without openings. How do we simulate this white column model? So this is on the left-hand side. It is an actual wall. By the way, this is from one of the publications that I shared with you. This is a work by Kiran Rangwani, alumna of the LD College, who did the master's MTech at IIT Gandhinagar. And I believe now she's completing her PhD in New Zealand. So left-hand side, it shows the actual confined masonry wall. You can see masonry portion and AM, and AC is the tie column portion, shown with black. So how does the white column, property of white column for that wall look like? We have the area of masonry, which is we actually need to create a transform section that would have a property of masonry but would take into account concrete. We don't take into account, please note this, in white column model, we don't bother taking into account reinforcement. If we have a reinforced concrete structure, we transform section for reinforced concrete section, for reinforced concrete, let's say column or beam section, would take into account property of concrete plus steel, isn't it so? Here our transform section is taking masonry and concrete. Steel is ignored. Why? Amount of steel is very small, it wouldn't make a difference. So we don't bother about the things that wouldn't make a difference, because one of my other principles is the more calculations you make, the more chances are there that you'll make a mistake. So let us focus on the big things and model them, and we should get good enough results. So here we have the masonry section on B, which has, like you can see, it's like I-shaped section. So the thickness of this, the flange is equal to the thickness of the wall, and the size of these webs, web is AM, web of the I section, and flanges are equal to N times AC. So N is the modulus of ratio of moduli for concrete and masonry. So let's say it could be 10 times, more than 10 times. It could be like 20 times, because masonry, usually, particularly brick masonry in India, will have very small modulus of elasticity. So this N value in case of this transformation will be definitely higher than 10. I know for concrete, we usually consider 10 as a good number. So you don't need, in reality, if you're doing SAP model, all you need are geometric dimensions of this transformed section. So you don't need to calculate I, you don't need to calculate A. This is only if you are of the transformed section. This is only if you're doing some kind of hand calculations, but I've shown that anyways. So all you need to do is to find N and to multiply N by the actual area of cross section, and then find what is the width of this flange, so that this area would be equal to N times AC. You can assume that the thickness of that flange is equal to a thickness of the size of the tie column. So okay, that is it. So here are some diagrams which are actually coming from Professor Juan Jose Perez Gavilan. He and I and a few other colleagues organized the first, I think, confined masonry short course in India in 2014 at IIT Gandhinagar, and these are some of the slides that he or they used in Mexico for this modeling. And here is a little bit more details about what do they recommend for taking as equivalent effective width for this modeling of horizontal elements. You remember we talked about that. So we need to take some effective width. It is the same as theory of reinforced concrete. In fact, it is coming from reinforced concrete structure. These are some just Mexican recommendations because this thing effect for modeling purposes is usually not part of the codes. So you will not find this definitely in Indian code, and most often this is not a part of the concrete code. So I would say for modeling purposes, you can take this recommendation so that this thickness or the width, equivalent width of this of the tie of this equivalent width of the beam could be taken as what is shown here for these diagrams. You can see a situation with the beam and the slab, and then only the slab. So these are two different cases. I know in India you would probably have the case where you would have a beam and a slab. In Mexico and in other countries, very often there is no beam at this location. It is just slab, like a flat slab system. But in any case, options are there and recommendations are available. So these are now some recommendations for the parapet, showing the situation with the wall. That if you have a parapet element, this is giving you a solution for the parapet. It looks on the first hand similar to the previous slide, but it is not, in fact. So on the top level, you have only, in this case, there was only slab. So this is identical to the recommendation from the previous slide. But the floor below the top, you have parapet. So one way of modeling the parapet is to take into account in that beam, that portion of the beam model, you can take properties or the height of the wall. So you have then equivalent transform section between the slab and the portion of the wall, which again is a little bit complicated for entering all these different properties. The other way would be, as we will discuss, is to model slab as is, and then have a separate element for modeling the parapet, which would simulate the stiffness of that parapet, which influences the stiffness of entire wall. So here at the bottom, please note that the model for the parapet is that you have fixed base, then you have vertical element which simulates, it is like a small wide column, and then you have horizontal element which is rigid, but it has pins, two hinges or pins at the end. So it is like it does not transfer any moments. It is just like a hinge element. So that is one way of, and as I said, there is more than one way of simulating these parapets. This is one possible way. And I will show here a few examples for wide column model before moving on to the equivalent, the other macro models. So the example one is again from that short course by Professor Juan Jose Perez Gavilan, and in fact, I can share he did also a sub model on that, but this is first of all, to show a building. So this is a simple plan of a simple two-story building with confined masonry walls. You can see always confining elements. Also very important to show confining elements always where you have them. So here you can see one wall with three tie columns, even though there are only there is no so that is an example of intermediate wall, and this is the 6 meter long. So this is dimensions in centimeters. 300 centimeters is 3 meters. And in any case, two-story building properties, masses of this building are known. I, in fact, need to share maybe this example separately with the text and model. So I'll share and create a zip document for your reference. So it will be shared with you later today. So how are these models labeled? So please note that we have these grid lines A, B, and C in vertical direction and 1, 2, and 3 in horizontal direction. In this case, this was modeled as a 3D model, but each grid line shows, each slide will show how walls on each axis were modeled. So for example, we'll start with axis 1 here on the top, horizontal. And let us see, you can see you have a wall and then you have two window openings. This is how it is modeled. So this is the actual wall on the left-hand side. This is the model. So the model is with one, the dashed vertical lines are showing the the wide columns. So you can see this wide column going along the center line B, so coinciding with the B. And then red horizontal lines are showing rigid links and or rigid beam elements. And then dashed lines are showing, horizontal lines are showing the slab elements. So let's call them slab elements or beam slab. Oftentimes we call them beam slab. And you can see here also identification on how this element looks like because it's end of the building. So it's L-shaped in a sense. You can see on the top T2 element. So anyways, all these elements have been modeled. And you can see here an example that how this hinge was the horizontal element at the location of parapets was modeled at both ends with the hinges, so that there is a rigid beam element at the location of the wall, and then there is hinge so that there is no moment transfer between the parapet and the beam. And then this short dashed vertical column is showing the parapet model that is along the lines of one of the previous slides. And you can see at the bottom sections of these elements. So for the white column with a parapet, that is C1. For the white column that is modeling the wall, that is C2. And then the right-hand side is the same as left-hand side. So you can see that this white column for the wall takes into account three tie columns and basically two wall panels. So you can see that. Then we are going to the similar. It was done at the grid line axis 2. And here it is simpler. We have just, there are no parapets, but there is one, you can see C2 at the bottom. That is the white column property. And you can see the slab property at the second or above the ground floor. It is T4. So you can see it has a beam and a slab. And also at the top level, it is beam and the slab. So there is a beam running on top of this wall. So that would be similar to what I would expect to see in India in similar situation. So all these models have been, all these walls have been modeled. And then we have axis 3, which is similar if you look at the original slide, at the original plan. Axis 1 and 3 are more or less the same, so there is no need to discuss. We already discussed axis 1 and axis 2, and we will now discuss axis A and B and C, which are in the other direction. So this is a nice way of showing it. So axis A is showing a solid wall. So now the question is whether we could take it as one wide column or two wide columns. In this case, there are two wide columns, as you can see, with the dashed black lines. So one for each panel. One could argue that it would be possible to model it as just one wide column. So as I said, modeling, first slide is modeling is a combination of art and science. So some other engineer could model it as one. And in this model, Professor Juan Jose decided to have these rigid links at the top level, at the other floor level, and then he added a rigid link to connect to the elm of axis 3. So because if you look at axis 3, which is meeting this, so this point at the left-hand side, this pin along the grid line A, meets with the model at grid line A. And that is considered to be good because they are creating this 3D. It is a 3D situation, isn't it? So maybe this wouldn't be needed if you were doing a 2D model. But because there is a 3D model and axis A and axis 3 meet just here, I don't know if you can see my mouse, axis A and axis 3 meet at this point at the bottom left corner. That is what it is modeling. So everything has to be connected in a sense. It is not, you can't independently consider these two directions if you have a 3D model. So axis 3 and axis A and axis B. Axis B has just one wall, which is shaded here on the left. So it is just one white column. This is a very simple model. And it has a rigid rigid beam at the portion where the wall is. And then after that, it is just a simple beam element without a slab. So it is just modeling a beam. So that is the model. And then for axis C, it is the same as axis A. So axis A and C. So it is symmetrical building in two directions. And you can see again the same story that I explained for axis D. One thing that Professor Juan Jose mentioned in his lectures and his modeling approach is that he does not, even though these are, he models in some cases this as an alternative to this white column model. He models these walls as plate elements, and he does not use very fine mesh in his modeling, but that is a different story. Anyways, the purpose of this and that whole example is on white column model, so therefore what you see on the right-hand side is what is modeled in this. And here are the properties of all these models, of all these sections, C1, C2, which are white column, then C3, C4, and C5. They're all shown here, the geometric properties like they were entered into the model. And finally, this is continuation. This is for T elements, and T elements are the slab beam elements. So it is showing what the geometry of these elements, and you can see this effective widths. For example, for this T4, you can see that effective width is about more than 70 centimeters, and the thickness of the beam is, the thickness of the slab is 12. So I would say if you go for T4, see, it would be roughly 6 to 6.5 times the thickness of the slab. So anyways, this is all following the guidelines that are shown at the beginning of the first slides. And then the model looks like this. So this is a 3D model, how the 3D model in rigid with the white column looks like. And you can see different colors. This is very nicely done for exactly the same as shown in the diagrams before. So it was very meticulously done model. And definitely there is no reason why not to share. It was already shared with the students in 2014, so we can share now. So the next diagram is showing the deformations of the model. The model was analyzed by response spectrum analysis. And this is just showing deformed shape, so you can see how everything works in unison. So the main point I would like you to take from here, actually there are several points about modeling certainly, but the point is that you can see that there is no separation between tie columns and conch and the masonry. So one wall is this, it is a single wall, always in single element, in this case modeled as a column, and that simulates the composite action of masonry and concrete. So there is no separation between masonry and concrete in this model. And this is exactly the same how the model would look like if we had a reinforced concrete wall structure. If this building at the beginning was just made out of reinforced concrete, model would look exactly the same. The only difference would be the geometric properties. There would be no need for transform sections for these for these wide columns. But model, if this was reinforced concrete shear wall structure, it would be exactly the same. That is very important to keep in mind. I know this different switch. It needs to be there needs to be a switch in the thinking because of such a wide use and educational spread of this concrete frame technology, which is, of course, it's understandable. Education has to follow what is there in practice. So this is the model for this SAP 2000. Now will be simpler models in 2D. Two more examples based on the work by Kiran Ragwani. And she actually did the simple models for her thesis, and was done in 2016 at IIT Gandhinagar. A thesis is also available, but what I am going to show some highlights. So the purpose at that time, this was the beginning of any analysis of confined masonry in India. So she was doing parametric studies on wall with the G+2 wall with one panel and with two panels, and modeling them in different approaches. And then she was doing walls with openings. So now, in this case, she modeled and we tried to see what is the difference in the results based on different modeling approaches. So in this case, you can see on the left-hand side, you can see actual wall. So it is confined masonry wall. On the right hand, on the middle, it is FEM, finite element model. So it is all modeled as a plate element. And then the third one is WCM, is wide column model. So the main purpose was to check what is the difference in behavior in the response of finite element model and wide column model. She was doing static analysis mostly for this and applied lateral load similar to, that would simulate the shape of earthquake loading. And you can see wide column model here. The center line is the center line of the wall, and then we have rigid. There are only rigid elements on the left, and because there was no rest of the building. It was not a building. It was, and then what she was doing as a parametric study is also aspect ratio. So, for example, height to length ratio at one floor level. So 3 to 4, 3 meter high, 4 meter length. So 3 to 4 is 0.75. So she was also studying the effect of this aspect ratio. If we have a longer wall, what happens? If you have a shorter wall, what happens? That effect. So and then she did with the same thing with the solid walls with two I would say panels, or two panels at one level. So this is one panel, this is second panel, and then 3-story wall. So same thing, she was modeling as finite element model and wide column model. I would like to note that in finite element model, all elements are the same, but all the elements which are shaded, which are shown on the right-hand side, left-hand side, and the middle, which are tie columns, they have properties of concrete. So they're not column elements, they're not line elements, they're just wall elements, but the same plate elements, but just with properties of concrete. So in this case, in finite element model of FEM, there is no need for transforming the sections, but you need to change the properties appropriately depending whether it is masonry or concrete. Whereas in wide column model, she had to transform these properties. So you can see section XX at the bottom right corner, which is simulating the cross section of this wall. I would like to mention that this middle portion did not matter actually. So this middle tie column could have been ignored in reality, but she did model it. So that was how the section that she used entered into a SAP. She did SAP analysis in her model, and these are some properties. It is all explained in the paper that I shared with you, and her thesis, of course, more extensively. And then she applied seismic loads and the same pattern as it would be for distribution of loads according to Indian codes, but the values of the loading don't have, I mean, they were calculating to be realistic, but in reality, it is more about comparison between the models than realistic forces and displacements. We try to make them realistic anyways, that they're not extraordinary, but it is not so significant. So for the fine, you can see the differences in shear forces and bending moments for a finite element model and white column model. There is practically no difference. Shear force and bending moment, they're the same, whether it is finite element or white column model. This is the form shape for a white column model, for finite element model, and for 1 and 2 grids. And then and then for a white column model. So both cases, for the same wall, finite element white column model, then finite element white column model. And on the next slide, we have differences in displacements or drift level for these models, and you can see this is circled the model that I've shown before. So you can see practically there is very little difference in both. There is some difference, but very little in displacement. So definitely white column model can simulate very well. I mean, it's very similar to finite element model. We are not claiming that finite element model is absolutely accurate, but let's say it is more accurate and more sophisticated modeling approach. So that is for sure. And then the other thing that we try to, that Kiran tried to check is the stiffness, effective stiffness. So she was taking force resultant at where it belongs, at the height of high H effective, and then what I want to say is and then that was compared, so it was effective stiffness of the structure, so force versus displacement at that location of the resultant, and then there is a corresponding stiffness for model W, the one that we were showing. That is there is a difference. So on the left hand side is finite element and white column model, so you can see that they correspond very well, and stiffness is the same, so which makes sense. Displacements are okay, then the stiffness must be okay, so that makes complete sense. So overall, the conclusion was that the white column model simulates very well behavior of models without openings. And then the third one is wall with openings. She did the model of that, and she tried to use again white column model and finite element model. So you can see this is a wall with window openings, with several window openings, and it has tie columns at the opening locations, vertical tie columns at opening locations at the ends of the wall. So she again modeled that on the left hand side. This is a finite element model, again the same approach. There is no line elements, there are no frame elements. All the tie columns are modeled as same as masonry, but with the concrete properties. And then this is her model for the white column model. You can see that she used, similarly to the models that proposed by Professor Juan Jose, is that for the parapet portion at the bottom, certain iterations were there, and it was found out that it is most important to simulate parapet at the bottom. So there were no simulation of parapets at the second and third floor level, just at the bottom, and that gave the best results actually, and it made the most sense. So that is good because it was not needed to model the parapet. So you can see again all the colors of these different white columns, different colors, and red color is that rigid link or rigid beam. And in the next slide, she showed sections where she was comparing the results. So this important section is the one at the base, because that is the maximum forces are at the base, and there is a section S1 and S1N1, which is at the location of openings. So That is where she compared
excuse me, ma'am.
forces. Yes?
Excuse me, ma'am. Your presentation
Sure.
is not visible, ma'am.
It's not visible at all.
No, right now, from last two slides.
Oh, seriously? Okay. Oh, thank God it's not just from the beginning. Okay. Oh,
No,
wow.
no. It was visible.
Okay. I'm not sure. I didn't do anything, Chaitanya. Okay. Maybe, you know what? I did disconnect something. Is it now visible?
No, ma'am.
Oh.
Yes, it is visible, right? Okay.
Okay, so I disconnected my other monitor. Okay. So
Yes.
which slide, can you tell me? I will repeat because these slides are important and graphical. Which slide was the last that you see?
But this is example number 3. Right.
Okay, start from there. Okay, perfect. Thank you for letting me know. I thought it was the whole. I thought it was, I've gone over 40 slides. Okay, thank you. So example 3 is wall with openings, again by Kira. That's part of her thesis, was a part of her thesis. So this wall had the openings at the windows at, you can see at all levels. And that is again modeled in the same way as what I showed before with white column model and finite element model. Finite element model, FEM, shown at the left, same thing. It is all plate elements, but then it is very fine mesh that she used, but I don't think it is necessary, but anyway, she used very fine mesh, and that was then these tie columns were modeled as concrete, and masonry was modeled as masonry, so that is the only difference, but it is the same type of elements that is important. So the colors look different just because of the mesh. And then on the right-hand side, our white column model approach, and you can see what I mentioned, and you couldn't see that at the base only, at the base level, at the ground floor level, these parapets were modeled. Some of her other analysis showed that it is not very relevant, very influential to model parapets at a higher level, but at the base it was important in this. At least I'm not sure if we can generalize this, but it made the difference to model or not parapets in white column model. Okay, so then she showed here it shows the sections, the levels at the building on the right hand side where the comparison was made between the two models. So obviously the forces are largest at the base, so section S1 at the bottom and S1, N1 at the location of openings, also at the base at the ground floor level were compared. And then here is the comparison. So you can see, okay, these are axial forces, S1, N1, this is location, the difference between finite element and the so this error shows the difference between white column model and the actual value. So the difference is less than 1%. So it was also good comparison of forces. Similarly, for moments, it was shown that for S1 and 2, which is at the level of the S1 and 2, the middle one showed it is the base level, but the middle wall showed a higher difference. It was about 10% difference in bending moments compared to the actual the result that it should be there, but the end walls are okay. So, and then this is the deformed shape. The difference in the form shape for a building over the height for the finite element model and the white column model. There is some difference, as you can see. There is difference in displacement. Please note that these displacements are very small. These are measured in millimeters. So this difference is very small in millimeters, but percentage-wise, there is a difference, certainly. And the difference could be attributed to this modeling of parapets and the fact that these models had openings. In the models without openings, there was no difference in displacements. So this is a difference in effective stiffness. You can see that the finite element model is giving a stiffer model compared to white column model. And again, it is a matter of modeling all these other elements like parapets, because in a finite element model, parapets are modeled. Here is from the reference finite element model. That is how it was calculated. Anyways, that is it. And here are all these different. There was a master's thesis in Mexico done under supervision of Professor Juan Jose by Taveras in 2008, and he was comparing all these different white column models with different levels of sophistication of models with these parapets in walls with openings and the accuracy. And so he compared that, and it was more extensive study, particularly on walls with openings and with white column model. So this model, what I would like to say is that out of these 4 models, 3 of them are pretty complex. The model at the lower bottom corner, model FR3, M1 FR3, is simplest. The model M1 FR3 is actually not modeling the parapets. So you can see that that model only models the walls without parapets, doesn't take into account parapets, whereas all the other 3 models take into account parapets. Model FR4 is similar to what Kiran did in her thesis. She only modeled parapets at the ground floor level. So it's interesting. You can see that these openings complicate, I would say that is a comment, make these white column models more complex. So observation for solid walls shown that for solid walls there is really identical results, whether it is finite element model or the white column model. In walls with openings, point 2 here is that the axial forces are very low. Obviously, that is not expected to be different, but shear force and bending moment values, shear forces are the difference is only 1%, and bending moments are up to 5 to 10% compared to finite element model. And displacement and stiffness are different, and the difference is in some cases up to 20%. So obviously, the fact that white column model does not model complete stiffness of the building result in this error. Conclusions regarding this white column model approach is this equally effective for simulating response of walls without openings, and is appropriate for routine design applications, but it is not able to accurately capture displacements and stiffness in the walls with openings. Hence, for detailed analysis of confined masonry walls with openings when complex load paths are involved and displacement stiffness are important aspect, then white column model might not be most appropriate analysis method. In any case, I want to add additional comment. Since masonry buildings in general and including confined masonry are rather stiff, rigid, their displacements are not very large, and we are never close to the code limits of displacements. I would say that modeling displacements accurately may not be priority in confined masonry buildings. If we are, the time is an issue, and time is always valuable in modeling, then it may not be, it may be okay to use white column model without sophisticated details for modeling parapets, and we will get correct forces for design, and ultimately we design for forces in linear elastic analysis. That is, forces are important for us for design according to the code, and for making sure that the walls are adequate for strength, because as I said, displacements are not going to be an issue in confined masonry walls. So this is just to show, in fact, in numerous courses that I delivered at IIT Gandhinagar and also at CEPT University, students were doing projects of the entire buildings. And for example, tomorrow we will be talking about IIT Gandhinagar project. This is one of their hostels, I believe I showed it, and it is divided in blocks based on the seismic gaps. So students in the first class of 2014, when I taught confined masonry at IIT Gandhinagar, they were doing blocks separately, models of blocks. And then let's say one group was doing this block D, which is shown here. And you can see a model of the block. They used SAP 2000 at that time for modeling Later on at SAPT University, also ETABS was used. So they modeled the whole block with all the walls in a SAP 2000 using white column model. So this is extruded view. That's why you can see the walls. And so they got good results and were able to do analysis as students, master students in the course. And you can see here, maybe it's not visible now on the screen, but it's visible in the model. They have this rigid elements modeling, simulating, as we discussed here, rigid horizontal elements. I would like to say, even though this is not a topic today, and unfortunately we will not have time to talk much about nonlinear analysis, I would like to say that white column model can be used for nonlinear analysis in software like SAP 2000 in ETABS, but where in that case we would need to model hinge properties in these wide columns with springs, with horizontal hinges, with shear hinges, and with flexural hinges. And that was done. There is again important research done in Mexico by Professor Amador Terran Gilmore, and he actually published with his students and colleagues papers at in earthquake spectra. I have also those papers, so if somebody is interested in nonlinear analysis, I could add that as a resource. It's a very good paper, and it is showing how white column model can be used for nonlinear analysis, and they did that, Terran Gilmore. So I can share that as well. I shared 4 papers, which are mostly like my students and colleagues, but I can share this paper. Is really good, and one of the rare papers that shows modeling of white column with nonlinear analysis. So now that is all about white column method. Now we are going to move to Strat and tie method. It is based on the limit analysis. So it is very important to really understand Strat and tie method. Normally in engineering courses, Strat and tie method would be taught as a part of reinforced concrete design, and that's how it is taught in Canada, maybe USA. I know in Canada it is definitely part of the training for reinforced concrete design, because it is coming from reinforced concrete design first application. So what does limit analysis mean? It does not mean ultimate limit analysis. It is limit analysis that is looking for capacity of the building. So it is a truss analogy approach, which is similar to that used for shear design of concrete and masonry structures. And the concept was developed by Swiss and German engineers in the 1890s. And it is, again, more work was done again in Germany at the end of 20th century by Schleich. He was a professor at Stuttgart University. He wrote books, papers, and he extended that method for entire structures, because initially it was just for localized areas. So here I would like to say, before explaining the method, that it is included in the confined masonry code. In India, it is in section 7.3.10.3, and it is mentioned as alternate method, Strat and tie method, and it says that it can be used for determining the shear capacity of confined masonry walls. This method provides a rational and consistent design approach for idealizing complex structural members with an appropriate simplified truss model. So that is what I want to say. It's not mentioned as modeling approach, it is mentioned as a design approach. So what is the concept? The concept is truss analogy, to visualize a structure subjected to external loading like a truss-like system, where compressive forces are resisted by concrete struts or masonry struts, and tensile forces are resisted by steel ties, because steel can take tension, and these are tie elements, and struts and ties meet at nodes. So this is a simple way of modeling one confined masonry wall as a strut and tie model. It is important that this is a truss model, so there is a pin connections at the nodes, and that in this case, because the loading is coming from left to right to left here, this green element will be a tie because it is taking tension, and the other blue elements are struts because they are taking compression. But if we change the loading and we applied it at point B in the other direction, then AB would be the tie and the rest would be the struts. So the first message is that this model is dependent on the loading. It is not a unique model for any loading. It depends how you apply loading. So struts and ties will depend on where the loading is applied, at which node and which pattern it is. So it is a bit complex that way, and it requires thinking and understanding of the structure. It is more complex than just modeling. So the design approach would be to first create an idealized truss model, then to find external member forces, struts, and ties due to that external loading, and for tie members, to design reinforcement in tie columns and tie beams. This is now intended for confined masonry walls. And for strut members, to check shear resistance for masonry walls and check compression resistance of reinforced concrete tie columns and tie beams. So that is how this should be applied in confined masonry. Because this number 3 is to design reinforcement tie columns and tie beams, it will assume that the first, that there is a limit state has been first achieved in tie columns and tie beams, and they were subjected to yielding as an ultimate state, and that will govern the capacity of that structure. So here is an example in the paper which I co-authored with Professor Juan Jose Perez Gavilan, which is included in your references. You will see a detailed analysis of that building with the openings, and you can see how openings are located. They're zigzag manner, they're not aligned, not nice actually, but it was done on purpose. So you can see how strut elements are shown in red, whereas tie elements are shown in blue or black. So this is for this direction of loading. For different direction of loading, it would be a different model. So it is a rather complex modeling approach, and it is mostly intended for in the context of confined masonry when you have significant openings, unusual openings, which you cannot easily model with wide column model. Because if you look at this wall, in this particular example, you would not be able to model it in wide column model. Why? Because the wall is not continuous. You cannot have a vertical vertical column here, or you cannot have it anywhere because it's not continuous. So this strut and tie model is a way out if you don't have. Now the question is, can you always see where are the struts, these diagonal struts, and where are the ties? Sometimes it is necessary to do first finite element model, and that was explained in the work by Kunal Gaisas and others in 2017. That paper is also available. So Kunal was also an MTech student at IIT Gandhinagar, and he did his thesis on this topic in 2017. And some of the work from his thesis is presented in the paper. It was published again, so you can read it. So he showed here finite element models of walls, and then how he would suggest these struts and ties. So you can see clearly at the bottom left corner how these struts are looking like. So struts are in the area of predominant compression, and then ties would be horizontally, and horizontally this would be also strut, and ties would be where we have tension. So finite stress distribution, which is obtained through finite element model, is very relevant here. So that is, as I said, showing a complexity, and he showed the variation of location of openings within a wall and the size of openings. So he was doing research practically. That was, of course, that's why the thesis is there. I'm sure some of you will be doing the same thing. So what are the advantages and challenges related to strut and tie model? Advantages are it is simple method because truss is the simplest system if you think of it, simpler than the frame system for analysis. It is transparent analysis. It is easy to identify mistake. It is suitable for manual calculations, but it can be done using computer-based analysis. And main challenge is it may be challenging to develop an appropriate model in complex cases. So it is, as I said, not simple. It requires engineer with this understanding of the structure and distribution of internal forces in the structure. And if there is no such understanding or experience on the side of engineer, then it is necessary to first develop a finite element model of that part of a structure to get a sense for it. The other type of models that look very similar, but it is actually not strat and tie, is something that I worked on with my student, former student Nikita Rankavad. She is now a consulting engineer in Ahmedabad, but she did master's thesis in, she did actually in 2018, I think this was, no, she did also in 2016, sorry, but the paper was published much later. It was published last year. So she did a modeling approach. Let's say this is a wall on the left-hand side. So she tried to model it as a truss model, but to use nonlinear analysis like equivalent static pushover analysis. And so she modeled the properties of the plastic hinges for the model. So the purpose of her modeling was nonlinear analysis, not linear analysis like Kieran's thesis. So she tried the model with one diagonal element and two diagonal elements. We called that 1S, one strat model, and 2S, two strat model. And the point here I want to mention is that she explained the results of this this model looks similar to the strat model for equivalent strat model for example reinforced concrete frames with infills, but it is different. First of all, that there are pin connections, and secondly, the way the properties of the strat are determined is different. It's not empirical. It is based on modeling this truss as to have equivalent stiffness as the wall. So it is the stiffness of the lateral stiffness of the truss corresponds to of the strat member corresponds to the stiffness of the wall. So that is a big difference, because as you know, and in Indian code, for example, you just take the width of the strat as assigned something empirical, but this is not empirical. So these are some of her results, which I believe I'll show later, but most importantly, I want to show the concept. So this is showing what I was talking about, this equivalent strat width. So you can see that it is coming from the stiffness equation of the wall. So we make this 2D strat equivalent to the stiffness of a masonry wall. And that's how the equivalent width of the strat member is calculated, and K is the stiffness of a masonry wall, which takes into account both flexural and shear component. That is a big difference, and this is all published in the paper Rankavat in 2021, which was published in the Engineering Structures, and I'll share that paper. That paper was shared with you already. So now here is a bit of complexity that comes with this model, how it was understood. So first, if you have gravity loading without seismic, then each of these vertical struts will work, and they will take a portion of this that is assumed. They take gravity loading, and there is no gravity loading in the tie columns, but just in these struts. Now, if you apply seismic force V in the middle, and then by nature of the force distribution, in one of these struts that is going from left to right, there will be an increase in the compression forces, and you can see now compression due to gravity in addition to compression due to seismic. However, in the other strut, there would be a decrease in compression because actually seismic load would cause tension. So at the end of the day, at the bottom, we can see only one strut. Why? Because this other strut developed tension. So once the strut develops tension, it gets out of the model. So that is how the model was developed. So the strats are only taking compression. Definition of strat is that it is taking compression. So this is a complexity, and it is possible only with nonlinear analysis to identify a point when this strat would be eliminated. But that is the assumption of the model. For the plastic hinges, she assumed that there is for shear, which is critical for this case. She assumed similar behavior like what Professor Juan Jose explained before, and that was force deformation behavior for the strat, that there is a first initially linear stage, then start of cracking, then maximum ultimate capacity, and then the failure. So this was all simulated in a model, and actually there is this is so-called backbone curve or force displacement curve, which is an input for the nonlinear model. And she used some of the parameters from, again, Mexican research, but an older research by Alcocer and it is Alcocer and Flores and Alcocer, and she used that as the properties of her plastic hinge in the model. And then she also she tried to validate this by the research from done at IIT Kanpur by Professor Vaibhav Singhal and Professor Durgesh Rai. It was PhD thesis by Vaibhav Singhal, and they tested some confined masonry walls, and she simulated the walls with this model, and the results are shown here. So experimental model is red, and then these are different options that she used with the one strat and two strat models. So you can see the two strat model, which is shown in blue, simulates better the behavior, but it kind of estimates some of the particularly maximum strength. So I think it's all a matter of calibration of the model for sure, but anyways, that's what she got. And with one strat model, which is shown in green, after the maximum peak value, she gets much sooner the failure of the model. So this is force displacement curve, which is obtained as a result of nonlinear pushover analysis, which she performed in SAP. So next, she also, in that same paper, you will see application, and somebody was asking, forgot the name, about simulating this for the building for your, let's say, assignment. See, this is how 2D model, she did a 2D model of one of the housing buildings in IIT Gandhinagar campus. So she basically took frames and then used rigid links to connect the frames. So it is the whole building, but it is just modeled in 2D. And you can see how many these truss elements she had. Wherever you have a wall, there is a truss element. And she also used judgment to eliminate some of the walls and ignore them if they were too small in the analysis, just for the sake of practicality. So anyways, she showed the results of this 3D analysis. And what is really nice, and I think this is the best value of this model, that you clearly see a mechanism of failure, how this structure fails. And you can see clearly at different stages these different performance levels according to the performance-based design. It's not available in India in the codes, but I'm sure it will be. So you can see that the bottom walls had the maximum damage. Critical walls are highlighted here, and they showed maximum damage in different stages of loading. And so she showed that first A is at a lower loading level, and then as the loading increases, she showed the increasing damage in all the walls. She did not see a collapse. In fact, she proved by analysis that the buildings were over-designed because it is also very nice, because it is possible. This is the capacity of the building on the top, looking at the normalized shear over the self weight or seismic weight. Let's say it was 0.4, and according to Indian standard, it was designed to 0.25. So the building, if the earthquake happens of the intensity corresponding to zone 3 in that location, the buildings would be perfectly elastic. They would not even achieve a nonlinear behavior. They could be pushed more to work harder, but this was the first application of confined masonry in India at IIT Gandhinagar campus. And so it is, I think, quite justified to over-design these buildings in that first application, and there was no code at that time at all. So as Mr. Anal Shah will talk on Friday, he was challenged as a design engineer with many challenges in that project. How seismic design is, this is the end, but just one more thought, or again, every time in the lecture, I'm putting in content from the code. Section 8 talks about seismic design, and it does not tell you which method of design to use. So you're free to choose. It just says that if you read this text carefully, and I encourage you to read, I will tell you in my own words, is that you have to simulate the behavior of the building. It says the structure shall be modeled adequately to simulate behavior of its critical structural elements. Elastic and shear modulus of masonry shall be used to reflect the axial and shear stiffness expected. Design forces and moments shall be obtained from the analysis using design loads and the corresponding load factors. A confined masonry wall should be designed for the effect of gravity loads and the effect of lateral loads. That is our topic of tomorrow's lecture. Then there is a section of advanced analysis methods. And it says that seismic analysis of confined masonry buildings 4-story or higher and buildings of up to 3-story height that do not meet requirements for the application of simplified method, which we discussed yesterday, shall be performed using dynamic or static methods according to IS 1893. Lateral load effects shall be determined based on relative stiffness of walls and wall segments by considering the effect of both shear and flexion in stiffness calculations. The analysis model shall take into account stiffness of floor and roof systems and any other restraints that may influence wall rotations. So there is no single word about which modeling approach to take. That is the conclusion. That is all for analysis. Further reading, there is 4 papers. I will add 5th by Professor Terran Gilmore, and I will share with you. I think it's a very good, excellent paper from Earthquake Spectra, published in 2009. And you have plenty of good reading materials if you are keen and interested in analysis and modeling, and that you should be at this stage, whether you're a student or a professor. This is something new, and limited research has been and practice has been done in India. So that is all regarding this topic, and I will stop sharing so that I can see you. And I hope you were able to see the presentation now in entirety. But I'm happy to answer any questions that you might have. And even tomorrow, if after reading and looking at more of these papers, we can discuss in more detail. So thank you very much. And I can put now my camera back. Were you able to hear me? My internet this morning was very unstable, but I hope that you were able to hear my voice clearly. Yes, and to see the slides.
Yes, ma'am. It was very clear.
Excellent, thank you. So any questions you might have now? I hope I try to clarify. It's a short, could be much longer topic, but we try to cover, as you know, in the course, many different topics, and every topic has its own time. So if please let me know if you have any questions now. As I said, you can come with the questions related to this tomorrow as well. We have 2 sessions together tomorrow, so try it, and I will share in the meantime the example also with Professor Chaitanya, so he can share with you and his team. So any questions, please?
Yeah. Dear participants, if you have any questions, please ask.
So my question is this clear? Are the models clear? Are they complex or simple? What do you think? I think this is new because if you were only modeling concrete frame structures, whether concrete or not, then many of these concepts are, I mean, similar, but in a sense new because of additional elements.
No, it was nicely explained, and I think more research is required. And basically, we try to we have to try to establish which method is good, and
Exactly.
yeah, that is. But it was nicely explained, ma'am. So it's very easy to understand.
It would be clear.
Yeah, Yogesh, please. Yogesh.
Ma'am, hello. Yes, sir.
Hello, Yogesh.
Uh, Ma'am, in strut and tie, is there any limitation of the inclination of the strut, like we have in reinforced concrete, same as in machinery also?
Yes, Yogesh, thank you for asking. In the paper which I published, I didn't include here, but in the paper which I published with Professor Perez Gavilan, which is on strut and tie method, it is there are some rules, and that is mostly related to height to length ratio of the wall. So if the height of length ratio is more than 2, that angle would not be basically we are ignoring that strut. So that angle is more than 50 degrees or something like that. So it comes from this ratio of, so the tangents is 2, isn't it, or height to length ratio? So it is corresponding to that. So if you have very narrow walls, that's what I was saying, a very short length, then a strut would not be very effective. So then we would ignore it. That is it may not be exactly the same rule as in concrete, but we put that rule for this or recommendation rather than rule. So take a look at that paper which is shared. It's Berzev and Perez Gavilan. In that one, it was explained the whole concept, and I'm not sure if it is explained in any other papers for now or books, but that paper explains it. It was a conference paper published in 2016.
Okay, ma'am. And we need to check the capacity of the tie as uh, reinforcement alone is taking the
Exactly. Yes.
detention, and
Yes,
concrete
you
is
have 4
ineffective.
bars. No,
Okay.
no, because you take only time. Well, concrete does not take tension. If it takes, we are very big optimists if you think the concrete takes tension. So we just take ties. So basically, you have scenarios. One scenario is that you have yielding in these ties, and that is the critical condition. So if you have yielding of ties and you have the force that is corresponding to that, then you find what is the corresponding capacity of the structure, because you have then proportionally need to increase the forces in the entire structure, and the resulting corresponding horizontal force is your capacity of the structure. See, it's inverse engineering. The other option is what happens if my strut governs. So you can find the corresponding force in the strut, and then again that force is not the same as the force that you got from the first analysis, because the first analysis was based on the applied loads, which are not the capacity loads. And then from that, again, reverse engineering, you can find what is the capacity. So whichever capacity you get as a smaller value for the entire structure, that is the one that will govern the capacity of the structure according to the strut and tie model. I see that you are familiar and asking questions about concrete, so you know from concrete part that how it is done. So that's what I'm saying, limit analysis. It's not limit states design. It is completely different animal, even though it looks the same. It looks like a cat, but it is a cougar or something. So, but this equivalent truss model, which you can call, unfortunately, there is a confusion even in the literature. The people who publish that, they still call it strut and tie model. Strut and tie model is specifically defined. It is like Coca-Cola. You know what is Coca-Cola? It's trademark. So this is for limit analysis. So that's why I wouldn't call the modeling approaches that can be used for both linear and nonlinear analysis as strut and tie. They're truss models, which of course can be used, and they're completely legitimate, but they really don't follow the strut and tie in the concept that they are looking for capacity. Because you can see the work with Nikita Rankavat, she started from 0 and then looked at different stages. So how can we call that strut and tie? that is the basic difference in these two approaches. Look-wise, it is the same.
And ma'am, this I think this strut and tie would be more conservative because all the lateral forces are taken by only one tie, whereas in wide column they are both the ties are transformed into an equivalent section. So both are effective, whereas in this only one tie column is effective when direction of lateral load is considered. When it is reversed, then means
Not really, because we will see in tomorrow's lecture when we talk about design for axial load and bending. Basically, you consider a section as two ties and the wall. So two tie columns and the wall. So the tie column that is under tension, even in this wide column model, will be the one that works most. You would have some masonry contribution there, which works, but then if it is under tension, masonry is also not good in tension. So it is, bottom line is the same, but it's just different distribution. And also in the if we use wide column model, then we will use this design approach as we'll discuss tomorrow. So we just consider composite section consisting of masonry and two tie columns, whereas here you just put this one tie column to work and you ignore masonry contribution. But on the tension side, in all the cases, it's going to be the tension steel in the tension forces in the steel that would be main contributors to this resistance. If you look at it, you will see tomorrow, Yogesh, when we talk about this, and then I will try to draw also a tie, the equivalent. What would it be, or how we would use the results of strut and tie model and compare them with this of composite section, which would be basically what we get from wide column model. Because in wide column model, as a result, you will get that bending moment, you will get axial force, and that is input for our design according to the code and according to any code that we do. These are good questions, very good questions. Yeah, it is. I would say it is conservative, but it is really giving us a good sense of the actual capacity of the structure. See, in Nikita Rankavat's model, she did all the modeling, and then she did hinges and all that, and she got that actual capacity, and we said that it is 40% of the weight. You can get the same by using limit analysis by strut and tie model, but just doing these two scenarios. One, what if a tie at the bottom where you have maximum force, that is the one that yields. And then what if the strut achieves maximum compression due to crushing value, which can be determined? What is the capacity? But let's say maybe if we forget the strut, let's go by the tie, and you get one value, and you can still compare it with this value that she got through nonlinear static analysis. So I would say these are two alternative ways of understanding what is actual capacity of our structure, not whether we can design it for applied loads according to IS 183, but what it would be the actual capacity. We want to know that as a designer or as a researcher. Code does not ask us to know, to find that out right now. Codes don't request us to find that out.
And ma'am, code does give any guidelines for compressive strength of the struts?
I will talk about that tomorrow. It doesn't, but it is very easy to determine. We have enough basis in the code, not specifically, not explicitly, but from the code you can find that out. I will talk about that tomorrow in the design part.
Okay.
So it would be easy. It would be very possible to do it if you want.
Okay. Thank you.
You're welcome.
Any more questions? Okay, over to Aditya, please. Aditya.
Yes, sir. I guess there are no questions from the participants now. So thank you once again, ma'am. Another extremely amazing session. The difficult-looking concepts of modeling were explained in quite lucid and comprehensive manner. I'm sure that it would be very much beneficial for all the participants. So thank you once again, ma'am.
Thank you.
That would be the end of our second session. We would be taking a lunch break now, and we will be meeting after half an hour for our third and final session of the day. So the link will be sent in the WhatsApp group. So keep yourself updated. We'll take a break for half an hour. Thank you. Thank you, everyone.